Hello and welcome to 8.1. In our trigonometry chapter, we are going to be talking about geometric means and most importantly the altitude and hypotenuse theorems. So for the sake of it, I'm just going to call this the altitude and hypotenuse theorems. Altitude, oops, that looks terrible. Altitude and hypotenuse theorems. Now we've worked with the Pythagorean theorem before. We're going to work with it. We're going to work with right triangles today, and we use this in exclusively right triangles. And sorry, just keep writing this. And we need to know something called the geometric mean. Now, and to stem from this, we have something called the arithmetic mean, which just means the average of two numbers. You would just say, for instance, I'll do this in pink. An arithmetic mean is something very straightforward, and we know that, for instance, 6 plus 8, or what's the average of 6 and 8? Well, what we do is we just add those two together and divide it by the number of terms there are. So in this case, there's two terms, so 6 plus 8 is 14, divide this by 2, and the average is 7, and that is what an arithmetic mean is, because mean means average. Geometric mean is a little bit different. It is the proportional mean between two numbers. So, for instance, if we took those same two numbers, 6 and 8, it is the proportional mean between it, meaning we would have to do something more like this. Arithmetic, I wrote arithmetic wrong. Arithmetic mean, and this is geometric mean. Looks more like this, where it's a proportion between each other. And what values would those x values be? If 6 was the numerator, 8 was the denominator, or vice versa. So as we know, we cross multiply here, we would get x squared is equal to 48. Then we would square root both sides, and we would get x is equal to plus or minus, and then we would break this down into two values. We would say 16 and 3, which breaks down to 4 root 3. Okay, so that's what arithmetic mean is, and we're gonna see variations of this in our example today. So, how does this relate to altitude hypotenuse? Well, I'm gonna start off drawing a right triangle, but I'm gonna draw it sideways, if Notability will cooperate with me. So, here's our right triangle, and an altitude, something we haven't really discussed yet, but an altitude, think of this as a mountain, and we got like some snow on the mountain, and then obviously, this is the very tip top of it. An altitude is the distance from the very top, or the vertex, down to the base. So this is our altitude, okay? And then we obviously know that across from the right angle is our hypotenuse, okay? And then we have leg 1, leg 2. For the sake of it, I'm gonna just put L1, L2, okay? And when we have this altitude, I'm gonna label this A, B, C, D, right? And when we have this altitude, we actually this point D creates, and it splits up the hypotenuse into two parts. So I'm going to call this part 1 and part 2 to coincide with leg 1 and leg 2. Now don't be fooled, part 1 does not equal part 2. Okay, it does not split it evenly, but something interesting happens. So I'm going to put some values in here just to help illustrate this better. Pretend angle A is 60 degrees, okay? And since we have a triangle here, one of them, the angle B is 90 degrees, making this 30 degrees, okay? And something that happens when you have an altitude is that since it goes from the vertex to the base, straight down, it actually creates right angles. So we actually have a new triangle here, And if you think about it, this blue triangle has a 60, 90, and a 30-degree angle. But don't we also have that for the big triangle? Isn't ABC also a 30, 60, 90 triangle? It is, which means that these are actually similar triangles. So we could actually complete this statement. ABC is going to be similar to, and I went from 60 to 90 to 30. So we have to follow that same order in the big triangle. This is our red triangle. Now let's organize this by color. Why not? So this is our red triangle. ABC is going to be similar to, in our blue triangle, 60, we want to follow that same order, 60, 90, 30. So 60 would still be angle A. The 90 degrees is not B, but it is D. And then the 30-degree angle is B. Okay? So we do have a triangle here, or two triangles that are similar. Now, something else happens, because if you look, we actually have a third triangle here. I'm going to do this one in green. And if you notice this time around also, we have another 30, 60, 90. Because if this angle here is 30, this angle here is 60. Okay? And we have another 30, 60, 90 triangle. So we have more similarity. So for the sake of it, I'm going to do red again, the red triangle. Triangle ABC is similar to triangle, and then the green triangle is going from 60 to 90 to 30, B, D, C. So let's organize this. That's our green triangle. And lastly, there's a third set of right triangles that are similar, the blue and the green. So I'm going to go ahead and label the blue triangle 60, 90, 30 again, just to keep this consistent. A, D, B is going to be similar to triangle B, D, C. Okay, so we have not a red, that should be blue, and green. Now, this is going to get messy, so bear with me. We're going to have a whole bunch of corresponding parts. Okay, we have AB is corresponding to AD. BC is corresponding to DB, and AC is corresponding to AB. That is a ton of information, but same thing here. I'm going to do the same idea. AB corresponds to BD. BC, corresponds to DC. And the last one is AC corresponds to BC. Last one, AD corresponds to BD. DB corresponds to DC. And then the last one, AB corresponds to BC. Now, what does this have to do with geometric mean? Well, if you look closely, I'm going to highlight some things. Now, let's do this in orange. Let's do this in purple. Well, if you notice, we have AB on the top and AB on the bottom. So if we took this as a proportion and set them equal to each other, wouldn't that create our scenario of a geometric mean where we have an x value that's same in the numerator and denominator? Yes, we would. So we actually develop an equation based off of this. Okay, if you look at AB in our triangle, AB is leg 1. So we could say, when we cross multiply these two, it's AB times AB, or leg 1 times leg 1, so we get leg 1 squared, right? Then, I just ran out of this room. So let's do this right below. I'm gonna bring this down below. Leg 1 squared. Now what's AC? If we cross multiply AC and AD, using the names that I've used here, AC, or AD is part 1. And then AC is the entire hypotenuse. So we actually have an equation to solve for the leg 1 specifically. Same thing also happens for the other 2 equations. Oops, let me do that. If you look closely, we have BC on the top and BC here on the bottom. So we could use our geometric mean, BC times BC, well, in this case, BC is our leg 2. So we could actually say leg 2 squared is equal to, and then we cross multiply this. AC is a hypotenuse, DC is part 2. So we can actually say part 2 times the hypotenuse. And these 2 equations are very, very similarly related. The last equation that we should see here is, and it's a little harder because I wrote it differently, BD is in the denominator, DB is in the numerator. They're the same thing because you just reorder the name, and we get a very convenient formula because BD is actually our altitude. So we could say altitude squared this time around is equal to AD is part 1, and then DC, cross multiplying, is part 2. And these are the 3 equations that we are going to use in this particular section. We're going to have problems where we're going to be solving for the altitude, or we're going to have a missing leg, or another missing leg, and we're going to be solving for parts of these right triangles. Okay, that's it. Know these 3 equations. I don't expect you to do all of this every single time. I would definitely recommend learning these 3 equations out. If you have any questions,